Hello everyone, and welcome to today's webinar, 3-Tool Coupling for Cabin Fogging Analysis. My name is David Bodine, Marketing Specialist at Thermoanalytics and host of today's webinar. Our presenter today is Dennis Hinz. Dennis is a thermal and CFD engineer at Thermoanalytics who performs modeling and numerical simulation for automotive applications. He started at Thermoanalytics in 2020 and focuses primarily on cabin and HVAC modeling. Dennis specializes in the development of cabin simulation methodologies, facilitating advanced coupling between software tools and human comfort modeling. He values strong attention to detail and the importance of capturing the relevant physics while making the optimal modeling assumptions. Dennis holds a BSE degree in chemical engineering from the University of Michigan and a PhD in chemical engineering from the Illinois Institute of Technology. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. We're also recording this webinar and we will be sending you the link following the presentation. And with that, Dennis, if you're ready, you may begin.
All right, thank you very much, David, and welcome everyone to the webinar. Hopefully everyone can hear me. David, please give me a shout if you cannot. Again, the title of this webinar is 3-Tool Coupling for Cabin Fogging Analysis. So we will begin with a brief introduction. We'll talk about how and when fogging occurs, and we'll lay the foundation of our problem we're trying to solve. We'll discuss the simulation methodology, and we will jump right into the case studies. So our first two are our extreme cases. So the first one is representative of our maximum warm-up case. It's a floor mode with 100% recirculation intake. Case 2 is the opposite side of the spectrum. This is more like a maximum defog scenario in terms of HVAC response. So this is defrost mode for the HVAC mode with 100% fresh air intake. From there, we'll start trying to narrow down an optimal HVAC response for the given conditions that we're simulating. And we'll conclude with a summary, discussion of future topics, and close with a Q&A. Okay, so first of all, when does fogging occur? So mathematically, this occurs when you have some air with some moisture content and you have some cold surfaces. And when this air comes in contact with our cold surfaces, if it reaches the dew point temperature, then condensation will begin to happen. And if it occurs on glass, then we see some fogging. So the application in the cabin is generally this occurs when we have cold conditions or rainy conditions, anything that generates some cold glass surfaces. We have a single occupant or maybe multiple occupants who enter the vehicle and they're generating some moisture into the cabin air from respiration or sweating and diffusion. And when this relatively higher moisture content air comes in contact with our cold glass surfaces, that's when we see some condensation on the glass and some fogging. So one of the problems for OEMs in terms of HVAC design is the question in a warm-up scenario, what percentage of recirculation air can we use, right? So in this webinar, this is going to be the focus scenario. It's going to be a warm-up scenario. And we'll be looking at identifying the optimal HVAC response for this scenario. So on one side of the spectrum, at 0% recirculation, this is 100% fresh air intake from the outside. So cold air from the exterior of the vehicle, relatively low moisture content. So in this scenario, of course, we have less fogging. We have a lower moisture content in our cabin air. However, we also have significantly reduced heating efficiency. So because we're taking in cold air into our HVAC system, it takes a lot more energy to heat the cabin at rate and to a degree similar to cases where we have a greater percent of recirculation. So on the other side of the spectrum, we're recirculating more air from our cabin, but because we're continuously adding moisture from our occupants, our moisture content is higher and we do see more fogging generally for these cases. However, we of course have improved occupant comfort and also improved heating efficiency. So there's definitely energy management concerns as well for a battery electric vehicle, for example. Okay, so the question here is, for this warm-up scenario, what's the optimal fraction of recirc air? Really, what's the optimal HVAC response that can minimize fogging, but also improve occupant comfort and energy efficiency? We can really simplify this further. It's really what's the maximum percentage of recirc air we can get away with for a given scenario. Okay, in terms of big picture, the big picture application is HVAC design and control. So can we use some of the results of our simulations to then drive HVAC design and controller design? Can these simulation results help us to develop a more sophisticated HVAC controller, one that's able to optimize safety, so defog, energy management, as well as occupant comfort? So we can imagine potentially, from vehicle sensor data, we have some humidity and temperature information, both on the glass and ambient. We have some idea of how many occupants are in the vehicle, how much moisture is being supplied to the air, and we have some additional information from simulation about the thermal behavior of our vehicle, particularly our glass surfaces. Okay, can we combine that then to provide some data points to our controller and help with this design? Okay, and the main topic of this webinar is to discuss this simulation workflow. So we have a simulation workflow here that can be used to obtain these data points to be able to obtain the optimal HVAC response for a given set of ambient conditions. Okay, so of course, one of the most important things in terms of the simulation workflow is to capture all of the important and critical physics. So the first one I'm pointing out here is that we need accurate local air temperature and glass temperature predictions. So if you recall, in terms of the physics of this condensation and fogging, it's important that we are able to predict accurately when we reach this dew point temperature. And you can see the distribution of temperatures here on our windshield. So local temperature predictions are very important. And what we generally use to obtain very accurate local temperature predictions for a cabin is our 3-tool coupling simulation workflow. So we have a coupling between GT, which is a system model for the HVAC system, CFD, and a thermal model. So from GT, we get very accurate vent and HVAC boundary conditions for our cabin. And then with the thermal CFD coupling, we get very accurate thermal predictions. Okay, so GT is providing CFD boundary conditions, so vent air temperature and velocity to all our vent inlets for our CFD model. And then CFD is providing some inputs back to our HVAC system model that it requires. So in this example, that would be the recirc air temperature is coming back into our intake for our recirc intake for our HVAC system model. Between the thermal model and CFD, we have standard thermal CFD coupling, so surface temperatures being mapped to the boundaries of our CFD model and convection data mapped to the surfaces of our thermal model. The next important piece of physics we need is the ability to track the cabin humidity over time. So for this, we're using a 1D cabin model in GT. So we're not doing any thermal simulation or thermal predictions with this 1D cabin. It's simply a moisture balance. And we can add our human moisture sources to this 1D cabin. Also, be able to consider different quantities of fresh intake and recirc air intake, and then be able to track the moisture within the cabin over time. So we use our human thermal modeling extension in TAITherm. We can import an occupant into our vehicle, and we can extract from the outputs our human moisture source that we can give to our 1D cabin. And then we can provide back to TAITherm a cabin relative humidity that we can use to simulate the condensation. For the condensation on the glass, we use our moisture transport model, which we can enable on the surfaces of interest, in this case, the glass surfaces. So we're actually solving for the condensation and the liquid film buildup on these parts of interest. Here we have a schematic of our GT HVAC system model. You can see we have a refrigerant loop and an evaporator. Of course, this is a warm-up scenario, so these are inactive in this case. Our heater here, so we're applying a heat rate to our HVAC air, and that's all feeding into our HVAC system, our ducting network, and our vents. Okay, again, all that is then feeding into our 1D cabin volume, which we use for moisture tracking. There's also a recirc air return here. So this feeds into our recirc door. So we have a fresh air intake, our recirc air intake into our HVAC system, and the door position here is how we are assigning our blending between our fresh intake and our recirc air intake. In terms of the thermal model, we do have a full vehicle thermal model. We have a single occupant in our vehicle, so we're using the human thermal modeling extension. We're solving for the physiological response of our occupant as well as sensation and comfort. Again, we're using the outputs from our human thermal modeling extension to calculate a human moisture source, and we're supplying that to our 1D cabin volume. We have moisture transport enabled on our glass surfaces, so we can solve for the condensation and fogging on our glass. And finally, because we're also interested in comparing the comfort between the different cases we're going to look at, we have a few different sensation and comfort metrics that we'll be looking at. So the first is PMV and PPD. PMV is the sensation metric in this case. It's short for predicted mean vote. You can think of this as purely an environmental metric. So it takes some inputs from the environment, air temperature, air velocity, relative humidity, and it translates that to some perception of sensation, right? So does it feel cold or does it feel hot? And this is a 7-point scale for PMV, from -3 cold to 3 hot. And then of course we can translate this into a comfort metric, PPD, so the predicted percentage dissatisfied. So what percent of people would be dissatisfied by this environment? Okay, so again, this is a purely environmental metric. This gives us an idea of how the environment is changing throughout the simulation. And generally, we recommend, of course, to look at multiple types of sensation and comfort metrics. The other one we definitely recommend is Berkeley Sensation and Comfort. So this is a more of a physiology-based metric. So it takes things like skin temperature and core temperature. Also, it translates the local sensation and local comfort for different body segments into an overall metric. And that's what's important here. The important thing to recognize is, again, we have scales for sensation and comfort, and we'll be looking at those results. So a 9-point scale for Berkeley in terms of sensation, -4 is very cold to 4 very hot. And then in terms of comfort, how comfortable do we feel in this environment? Another 9-point scale from -4, very uncomfortable, to 4, very comfortable. In terms of the fluid model setup, it's a pretty basic CFD cabin model. So we have some inlet boundary conditions. So our defrost vent, for example, floor vents, side vents, and then a pressure outlet in the back, as well as a recirc air outlet. And the interesting thing here really is how we are passing our vent data from GT to Fluent. So here you can see our vent distribution here in our GT HVAC system model. So defrost vents, side vents, floor vents, etc. And each of these is passing a temperature and a velocity to our Fluent model. Okay, so what's interesting is that new Encotherm version 2023, which we are using for these simulation studies, is we have the ability with a variable assignment task to adjust Fluent input parameters on the fly in an automated way with Cotherm. So Fluent input parameters are variables assigned or defined in the GUI, and you can link these to the boundaries, to the boundary conditions in Fluent. So for example, inlet velocity for one of these vents. And now Cotherm has the ability to assign these with a variable assignment task on the fly in an automated way. Here is a description of our warm-up scenario we'll be looking at. So this is our scenario, and we'll be trying to find an optimal HVAC response given this scenario. Okay, so our ambient temperature is -10°C, relative humidity of 80%. This is pretty typical of a cold winter morning in the northern United States. We first precondition our human to room temperature environment, so 3 hours indoors. Just get him used to an indoor environment. We then simulate a walk to the vehicle, followed by a 45-minute warm-up at speed. Okay, and here are some results from the 3-tool coupling from case 1. Again, case 1 is one of our extreme cases. This is our maximum warm-up case for this HVAC system in these conditions. So floor mode at 100% recirculation. And we have a pretty wide variety of data we can look at from our 3-tool coupling simulations. We have air thermocouple data, we have surface thermocouple data. In terms of the air data, this really comes from cell registers, which is what they're called in Fluent. So these are collections of cells, and we can take averages to get a good representation of what a thermocouple temperature might be at that specific location. So we have these dispersed around at head level and foot level within the vehicle. And here you can see the temperature results for our cabin. So head level in blue, foot level average cell register data in orange. Of course, in floor mode, our foot level temperatures are quite a bit warmer than our head level temperatures. Heater heat rate here from GT, and over here on the right, some surface temperature data. Of course, not all the data, but I'm highlighting some of the key data points here. Here you can see some images of the thermocouples placed on the interior, for example. So this is on the interior windshield. Plotted here is the door average temperature interior versus exterior. You can see the interior temperatures increasing over time during the warm-up. Exterior temperatures stay pretty close to ambient at speed. And that's the key difference here in terms of condensation and fogging. You can see for the window temperature, the interior and exterior temperatures are quite similar. And that's because the thermal resistance is very low for the glass relatively to the other material stack-ups throughout the vehicle, roof, floor, doors, etc. Those have a lot of insulation. So here, the windows are generally a pretty big heat sink for a warm-up scenario, for example. And that's why, because the temperatures stay cold, that's why we see a lot of fogging and condensation that tends to happen here. Okay, these are some of the results for the moisture. So again, we can take some outputs from our human thermal modeling extension. In particular, we take the evaporative heat rate and heat rate from respiration, and we translate that into a human moisture source. And these are not insignificant moisture sources here. So a single adult can output anywhere between 20 to 200 grams per hour of moisture into the cabin. We can take this human moisture source and we're tracking that in our 1D cabin in GT, and of course, calculate a cabin average relative humidity over time. And we'll use that to perform our fogging and condensation analysis. This is a summary of those results. We have comfort results and fogging analysis here. On the bottom, we'll start with the fogging animation. What we're looking at here is relative humidity, but the relative humidity at the temperature of the glass. So anywhere where you see 100%, so anywhere we have white, is where we've reached our dew point temperature. This is where condensation and fogging is occurring on the glass. So really what's happening here, I actually cut the animation off at 15 minutes, but after about 5 minutes, we have significant condensation and fogging really on all the glass within the vehicle. This makes sense. This is our extreme warm-up scenario, so it's 100% recirculation, so we're continuously adding moisture into the cabin air. That's why at some point, we just have consistent fogging within our cabin. So in terms of comfort, because it's the max warm-up scenario for this HVAC system and these conditions, it's also representative of our maximum comfort scenario. So we're looking at Berkeley sensation and comfort on the left, PMV and PPD on the right. I will begin with Berkeley. So sensation metrics are in blue, comfort are in orange. So what's happening here is that early on, we start with very low sensation, so very cold as the occupant initially enters the vehicle. We're warming over time, and then at some point we reach almost neutral sensation, so somewhere between 30 and 40 minutes. In terms of comfort, again, we start at very uncomfortable conditions, so very cold, very uncomfortable. We're warming up over time and we achieve something like neutral sensation somewhere between 20 and 30 minutes. And actually the trends are very similar for PMV and PPD. So in terms of sensation, increasing over time, achieving neutral sensation here, somewhere between 30 and 40 minutes. And then comfort, predicted percentage dissatisfied, 50%, so something like neutral comfort between 20 and 30 minutes. So it's always interesting to look at multiple sensation and comfort metrics. We're not going to go into depth about Berkeley, but we have some here with PMV and PPD, we have some idea of how the environment is changing over time on average. And then if we wanted to, we could look in more detail with Berkeley, how the physiology and the local body segment sensation and comfort are all playing into the trends. Okay, on to case 2. So again, this is our opposite side of the spectrum, the extreme case on the opposite side. This is maximum defog, so defrost mode for our HVAC mode, and 0% recirculation, so 100% fresh air intake. And I should mention that for these mode changes, the total flow rate does not change, just the distribution of flow to the different vents. Okay, so first we have our cabin average temperature plotted here, a comparison between case 2 and case 1. So case 2 is in blue. Case 1, our maximum warm-up case, is the orange dotted line. And this is an average of all the different cell registers, head level and foot level, dispersed throughout the vehicle. Of course, our case 1 is significantly warmer than our maximum defog case. Okay, so you can already see there's definitely some energy management and energy efficiency concerns here already with our maximum defog case. For the windshield interior temperature, so this is an average of these 3 interior surface thermocouples. Of course, our windshield temperature is quite a bit warmer for our defrost mode case. Okay, so you can definitely see this will help mitigate our fogging. It would require a much higher moisture content and a much higher dew point temperature for fogging to occur on the windshield in this case 2. Okay, in terms of heater heat rate and overall energy expenditure, case 2 again is in blue. In terms of overall energy, integrating these curves, almost double the overall energy expenditure for our defrost case. So again, you can already see there's definitely some energy management concerns, but we will, do a lot to mitigate fogging in this case. These are the two cases side by side. Case 1, our maximum warm-up case on the left. Case 2, our maximum defog case on the right. So this was our animation we've already seen. After about 5 minutes, we have consistent and significant fogging and condensation happening on the glass throughout the vehicle for the duration of the warm-up. On the right, we do mitigate condensation for the entire warm-up. So our moisture content stays low enough. We don't have any fogging occurring in this case. But of course, neither of these cases are ideal. This one shows a lot of fogging. It does show, the ability to achieve pretty good sensation and comfort over the duration of the warm-up. Also, much better energy efficiency. The comfort, the sensation and comfort for our defog case, you can see basically what we're seeing here is very uncomfortable, very cold conditions for the entire duration of the warm-up. So again, bottom line, neither of these cases are ideal. In the next few cases that we'll look at, we're going to be trying to find the optimal HVAC response for this set of ambient conditions in this scenario. Okay, that brings us to case 3. Case 3 is back to 100% floor mode and then 83% recirculation by mass. So we can start here with the fogging analysis, the fogging animation. So what we're looking at is for the first 5 minutes or so, we don't see much fogging on the windshield. After that, we do see some condensation, some fogging happening, more so on the exterior of the vehicle. We do still have a little bit of defrost vent flow coming in floor mode as well. So as the temperature of the glass warms up, you can see this fogging condensation decreasing a little bit over time. And to help proceed to the next case, this is probably pretty close to our optimal HVAC response. You can see we're doing a lot to mitigate some of this fogging for the warm up. However, it's not ideal. We still have some significant fogging here on the outsides, especially for the first 5 to 10 minutes. So what we can do is we can look at this in a different way. So I've plotted below here the dew point temperature in blue. So again, this is basically just the moisture content. So initially our moisture content is quite low and our occupant is entering the vehicle. So he's adding some moisture and then we achieve some steady state value as it blends with our fresh air intake. In red, I'm plotting the surface temperatures of our interior windshield. So these 3 surface thermocouples over time. And as for the analysis here, anytime this blue line, our dew point temperature, crosses over any of these temperatures, then we're going to see condensation. So we're seeing the same picture here as we see above, right? So after about 5 minutes or so, we see some pretty significant fogging, and then that starts to dissipate over time as the glass temperature warms up. Okay, so on this next plot, to help drive us and guide us to case 4, I've kept this same bottom line, so our kind of bottom point for fogging on the windshield. But now I've plotted these 3 additional temperatures. So these are the glass windshield interior temperatures, these 3 points for our defrost case from case 2. So you can see our glass temperatures are significantly higher for our defrost case, as we saw before. So we can definitely still play with our HVAC mode as well to try to find the optimal HVAC response. So not only our recirculation air percentage, but also our HVAC mode. So maybe we can use defrost mode early on in this period to help mitigate some of the fogging early on, and then switch to floor mode to then also help maximize our comfort and our energy consumption. So just briefly, we can already tell we're pretty close to optimal, probably, so the optimal HVAC response, but let's also look at sensation and comfort and energy consumption. So just briefly, this is PMV and PPD. The PPD is in orange, so the solid line is the new case, case 3, the orange dotted line is case 1. So you can see we're just delaying comfort by a few minutes by introducing some fresh air intake. In terms of energy consumption, it is a little bit higher, but negligible difference really between these two cases. Okay, that brings us to case 4. So in this case, we are changing the HVAC response a little bit from case 3. Again, we're introducing some defrost mode early on in the simulation. So for the first 10 minutes or so, we're running in defrost mode and then transitioning into floor mode. The recirculation percentage is the same as case 3. So we can again start with the animation. So for the first 10 minutes or so, we really do a great job mitigating this defog. We do have a little bit of condensation and fogging happening after the transition to floor mode. But then again, as the windshield temperature warms up over time, really that dissipates pretty well. So I'd say this case is fairly close to optimal in terms of fogging. And you can see, we can plot this again and see the same picture as above. For the first 10 minutes or so, we don't see any condensation, and a little bit, after the 14 or 15 minute mark, which dissipates over time. In terms of sensation and comfort, again, we're just delaying our comfort a little bit. We do still achieve good levels of comfort after about the 30-minute mark or so. We have delayed it by about 5 minutes by introducing some fresh air intake, also defrost mode for the first 10 minutes or so. In terms of energy consumption, again, a little bit of an increase, but overall, big picture in terms of comfort, in terms of energy management, and in terms of defogging, I think this case 4 is pretty close to an optimal HVAC response for this given set of conditions. Final case here is just to drive home the idea that, of course, when the conditions change, when the scenario changes, when the number of occupants change, of course, your HVAC response that is optimal is going to change as well. So in this case, we kept the same HVAC response. So a transition from defrost to floor mode after about 10 minutes or so, and then 83% recirculation intake into the HVAC system. Okay, so for the first 10 or so minutes, again, we don't see any fogging because we're running in defrost mode. But then after this transition, you could see, of course, significant fogging and condensation on our windshield. In terms of the dew point, we've added another occupant, so our moisture content being added to our cabin air is double. And of course, it reaches another steady state point as it balances with our low moisture content, fresh air, but we're sort of in a region here where we see significant condensation. So the bottom line with this case is, yes, we have developed here a simulation workflow that can be used to identify the optimal HVAC response for a given scenario, but to solve the full problem, we need to look at the full spectrum of operating conditions. Okay, so in conclusion, we saw that the cabin moisture content depends primarily on the number of occupants, the airflow rate, and the extent of recirculation. We can use our 3-tool coupling simulation methodology to predict local fogging as a function of cabin moisture content and local glass temperature. And we can use this information from these high fidelity fogging simulations to identify optimal control strategies and drive HVAC design. In terms of the future, here at TAI, we're definitely interested in advancing this humidity coupling simulation workflow. And one of the ways is, if you recall, we were previously using a 1D cabin in GT here to track our moisture. So one of the main ways we can improve this is to then solve for the local humidity within the cabin. Also, the local humidity that's entering and leaving the cabin. Right, so introduce species transport into our CFD model. So we're tracking locally now our humidity within the cabin. And instead of just passing the recirc air temperature to our HVAC system, we're also passing a local humidity, a local moisture content. And then from our HVAC system model, we're passing temperature, velocity, but also the intake humidity. So you can imagine when, in cases where we are running with some degree of fresh air intake, locally, the relative humidity, for example, at the defrost vents or near the windshield is going to be lower than the cabin average. Really, the moisture content, I should say, will be lower than the cabin average. Then in terms of thermal CFD coupling, we also want to introduce some coupling with the moisture So passing a near wall humidity and mass transfer coefficient from Fluent or CFD, and then passing surface temperatures and the surface moisture content to our boundaries in STAR. Thank you very much. That's all we had today for the webinar, and we can open it up for a Q&A session.
Yeah, we got a couple questions here. The first one is, can you modify simulation parameters, for instance, simulate a calibration?
I see. I suppose you are, you're talking about calibrating an HVAC controller, I suppose. And if that's correct, I think you might need to then create some reduced order models for this so they can run much more quickly to do that. But if you're also talking about calibration of your HVAC system, yes, absolutely. So ideally, you know, we've used a generic HVAC system here in our GT system model, but ideally this would be calibrated based on some bench test data or some manufacturer data. Yeah. So hopefully I answered your question in one of those two ways.
Second question I got here is, why did you use 0% recirculation for defrost mode?
It's the extreme case. So the first thing we did was just look at the two extremes, right? So you have one extreme, which is introducing the maximum moisture into our cabin, which was maximum warm up and then 100% recirculation. The other extreme scenario here is, you know, minimizing the moisture content in the cabin, so 100% fresh air intake. So the first two cases were just to look at the two extremes, just to see, you know, to bound the problem, you know, how different are the comfort, how different is the energy expenditure, and of course how different is the fogging between those two extremes. So it's really to build up the problem, and then from there, you know, we can see what an optimal HVAC response then looks like.
Can you simulate a passenger with wet clothes from rain or snow on the way to the vehicle?
That's a good question. Yeah, I think you could introduce some moisture content to the clothes. So in the workflow that I presented, we aren't coupling the, so I'll go back a slide. So we're not coupling the surface moisture with our air directly between TAITherm and our CFD in this case, or between TAITherm and GT, right? So we're just introducing a moisture source manually, and the moisture source we're introducing in that case is from our breath, right? But that said, yeah, you could also then adjust that source to extract different data from our human thermal modeling extension. You could extract the evaporation rate from the clothing or from sweating, just like you do with sweating, and you could adjust that moisture source to then include, you know, that kind of scenario as well. So adjust the moisture source based on different outputs from human thermal modeling extension. Yeah.
What is the runtime for these simulations?
Okay, so these simulations ran in about 8 to 12 hours. I will say though that these are lightweight. These are, you know, demo models. I think in a full production model, you could probably double that. So maybe a day or two. Yeah.
And is it transient coupling?
It is. Maybe I have an extra slide actually. Some references. Yes. Yeah, so this is the fully transient coupling workflow in this case. So each of the models is a transient model, GT, TAITherm, Fluent, and then we're you know, identifying a coupling interval. So in this case, 10 seconds, and then we're passing information between them. But each of them is running in transient. Yeah.
Let's see. Are there any validation results for 100% recirculation?
I'm sorry. No, we do not have any validation results for this case. So this was again purely lightweight demo application. We haven't worked with any of our customers to validate any of these the simulation workflow. Right. So we did. We have validated the 3-tool coupling methodology in the past. However, we haven't extended that to the moisture and humidity. Yeah.
What is the time step used in CFD simulation?
Again, we ran this pretty lightweight, so I think it's 1/10 of a second or so, but in reality, that should be decreased.
I think just we have time for one more here. In your further development of humidity model, you had a humidity transfer from 1D to 3D. Is this the whole humidity or some form of local humidity? And if so, how are you proposing to get local humidity?
Yeah, so I think you're talking about this slide. So in the previous method, yes, we use just the average humidity. So there are other things we could do, right? So let's just talk previous workflow, the workflow we're actually doing here. So we're doing a cabin average humidity, and we're passing that to TAITherm, right? You could do different things, right? So you could pass, instead of this downstream humidity, you could pass the humidity or the moisture content, coming out of the vents, for example, right? So that would be before it mixes with the cabin. And you could pass that, say you're running in defrost mode, you could pass a more representative humidity here to this windshield, for example, more representative of the actual moisture content coming out of the defrost vent, right? So there are things we could do to maybe improve this simplified method for a heavy defrost mode case, for example. But yes, in the future, we want to then identify species transport. So instead of just tracking the air velocity, right, and air continuity equation, right, we're also solving mass balance equations for the species. So the water species and the air species, right? So each cell will have a local relative humidity value in it, and also at the boundaries, you will be supplying a mass fraction of water, right? So the air at the intake of these boundaries will have its own moisture content. So that's kind of the idea for the future, is to be able to track then the local humidity, and then couple that locally with our TAITherm model, and also couple that locally with the inputs going into our HVAC system. Yeah.
Okay. That will complete today's webinar. We appreciate you all for attending. You will receive a follow-up email this afternoon containing links to download the presentation slides and watch the recorded webinar session. Thank you very much and have a nice day.